Good morning. So after all this technical trouble, I'm finally able to get started. Let me just say a few things about the title of this day. It's an introduction to imprecise probabilities. I remember being asked to do the basics. And basics, in my mind, can mean two things. Either it's very basic and very simple. This is not what it's going to be. It's going to be the foundation. It's going to be the basis of everything. So it's not going to be simple. I never intended it to be simple. I'm trying to be as untechnical as possible. I'm going to try and convey ideas, mostly. So I'm going to be talking about ideas. Now, first of all, this is maybe going to sound a bit facetious, but probabilities are not the best way to talk about imprecise probabilities. So I'm not going to talk about probabilities mostly. I'm going to talk about other things, because the reason for that is when you talk about probabilities, you have a fixed notion in your mind of what that means. And I don't want you to have that notion in your head, in your mind. I want you to start afresh. And so I'm going to, for dialectical reasons, start with something that is almost unrecognizable and then move towards probabilities in the end. So I think in the end of this morning, we'll probably hear me talk about probabilities in a real sense, but not yet. Yeah. So that's one thing. Also, initially, I was asked to give like a 4.5-hour stretch covering the basics, and Catherine was going to do, Catherine and a couple more was going to do the first hour. She was not able to do that for some unfortunate reason, and so I was asked to do this. So this had me scratching my head for a bit, but then I decided to, as an introduction, to do a few things that I did before in the SIPTA lecture, which turned out to be a perfect introduction for what I was going to do today. So I'll be repeating the first SIPTA lecture that I gave here this morning, and I'll be just covering very briefly all the topics that I'll be covering for the rest of the day as well. So that's going to be the first thing. Now, in this introduction to IP, this is what I'm going to talk about today. These are all the topics in a colorful mind map. So we'll talk about imprecise probability models, and they come in two varieties, two ways, two flavors. The one is the epistemic models. These are the decision-making models, if you want. And these come in three flavors. I'll start with desirability. That should be the top one here. Then I'll move to other models, and then after these other models, I'm going to say a few things about non-binary choice as well. So that is the first part of the day, and then the second part of the day will be about aleatory models. So these are epistemic, these are about some subjects' models and decisions. These are more, it's difficult how to classify them, but they're not really related to, or not directly related to somebody's decisions. They're more related to what we would call the outside world. And that's why I call them aleatory. You can call them frequentistic or frequentist as well. Yeah. I will give some time for Kevin to pan and follow me. I'm walking around quite a bit. All right, those are the topics for today. A few books. Teddy's already sent me his slide, and he's going to promote a number of books, and I'm trying to be a bit different and promote a number of different books. The one that started this whole misery is Statistical Reasoning with Imprecise Probabilities. This is Peter Wally's book. It's been out of print for quite a while, but it's still quite a nice book to read. Then there's this book, Introduction to Imprecise Probabilities, that we co-edited, a number of us here co-edited. Matthias Strofas and I wrote a book on lower revisions. This is more a technical book on some of the models that we're going to go into this this morning. And then there's something I'm only going to briefly look at, that is game theoretic probability models. These are very interesting types of models. I won't have time to go into them, but if you can get hold of a copy of this book, this is one of the more interesting books on probability and imprecise probabilities to appear in the last few years. Right, that's it for my introduction. Give me some time to switch to the second part. So I'm going to start talking about imprecision. And imprecision comes in many flavors, comes in many varieties. But before I say a few things, what I'm going to talk about today is not about me. It's about the work of all these people and many more. I've been fortunate enough to be able to be at the beginning of this, be there at the beginning of this and follow everything. But there's a number of people that I've worked with, that I've talked to, that I've listened to, and that and whose work I've read. And so I've tried to list them here. They will come back later on as well. So this is imprecision. Imprecision comes in many guises, in many varieties. Let me tell you about a few. Set valuedness. If you talk about imprecise probabilities, people typically talk about a set of probabilities, or all the probabilities between a lower bound and an upper bound. So the probabilities are set value. If you talk about the probabilities. If you talk about the expectation functionals, expectations, these are typically functionals, then these will typically then become nonlinear. Lower probabilities, lower expectations, upper probabilities, upper expectations will have a nonlinearity problem, whereas expectations, typical expectations that we know are typically linear. So nonlinearity is in a way associated with imprecision. When we go to decision-making models, then imprecision is typically associated with indecision, with not making a decision, or not wanting to make a decision, not wanting to make a choice. So that's another way in which imprecision appears. When we talk about logic, then imprecision is associated with incompleteness, with not having a full set of propositions, in a sense. And so incompleteness is also associated with imprecisions, as we shall see later on. And then when we talk about orderings, probability orderings, for instance, imprecision is typically associated with incomparability, not being able to compare two things. All of these things are negative. Set valuedness is typically the opposite of being precise, being single valued, which is something nice, whereas set valued is typically perceived as not so nice. And then what you see is, I have to go closer for it to respond. Now it's responded. So you have all these negative things: non-linearity, indecision, imprecision, incompleteness, incomparability. So that means, it's a bit annoying, can't we? Okay. Let me go here. So that means that imprecision is perceived as something negative. And that is not necessarily the message that I want to convey today. I want to convey today, and especially in this first hour, that all these negative things can designate something positive as well, something useful, something interesting. So that's what I want to talk about. Let me begin with what I think that you're most familiar with, and that is probability intervals. So typically when I have an event is, so I have some space, omega, possibility space, all the outcomes of some experiment, all the values of some variable that I'm interested in, and I'm uncertain about the outcome of the experiment, I'm uncertain about the value of the variable, and so I will have all this set of values, which is omega, and then I consider an event, this is probability language, and this event, here, this event is a subset of the possibility space. And I'm looking at the probability of the event, and I don't know that probability all that well, And so I give an upper bound and a lower bound. So the lower bound is the lower probability of A, the upper bound is the upper probability of A. And of course, since probabilities live in the unit interval, this red interval will be a subinterval of this black unit interval. So these are what we call upper and lower probabilities. And the idea is that the real probability the idea could be that the real probability is not really well known, but it's in between these two bounds. That's not very interesting. It becomes more interesting if you look at two events, an event A and an event B, as depicted here. Yeah. And so I give another bound, a lower bound for the probability of B and an upper bound for the probability. I'm going to ask questions about this. I'm going to ask, what's the probability of the intersection of A and B? So how do I solve this problem? Well, what I'm going to do is I'm going to look at the constituents of A and B. So I'm going to subdivide the space into four regions. The intersection, A minus B, B minus A, and then the complement of the U. So these are the four regions that are a partition of the possibility space that is there because of the two events A and B. I'm going to assign possible values for the probabilities of these constituents. So alpha, beta for the intersection, gamma for B minus A, and delta for the rest. And of course, since these are probabilities, they have to sum to 1. They must be non-negative. They're mass functions, probability mass functions in a certain sense. And what I know is, what I've specified is that the sum of A and B, that's the probability of A, must be between the lower bound and the upper bound. And the sum of B and beta and gamma must be between the upper bound for B and the lower bound. So that's what I know. And I'm, of course, interested in the probability of A intersection B. So that is beta here. So the question is, what is the range of beta? What is the lower bound of beta? What's the upper bound? So I get a simple linear programming problem that I can solve. And if I solve that programming problem, I get these two values. Who knows the name of these bounds? In precise case, at least. The maximum of. Anybody know the name of these bounds? They were first invented or first written down by Boole, George Boole, but he did it only implicitly, like much of his. He wrote a book on probability, and much of it is implicit. First one to do it explicitly was Fichet. So these are called the Fichet bounds or the Boole-Fichet bands. Yeah. So this is 1800s. So this type of probability is, or imprecise probability, is quite old. Fine. What we come to by looking at this problem is that what we see is that we have a probability, a precise probability on omega, but we have a collection of them, all the probabilities that satisfy these bounds here. So what we see is that we have bounds on the probabilities, and these bounds are inequalities. They are weak inequalities, which means that all the probabilities that satisfy them constitute a closed set. So we find a set of probabilities, a set of probability measures that correspond to this formulation here, and this set is closed. And it's also convex. Why? Because if I take any convex mixture of these probabilities, they will still satisfy the bounds. So all the probabilities that satisfy these bounds constitute a convex closed set. That is what we call, or will call, a Creedle set. So this brings us, this way of looking at things, brings us naturally to the notion of a Creedle set. So that Creedle set is, in this language, is just a closed, convex set of probability measures. That's what we call a Creedle set. Now, what we've done is, in a way, what we're doing is we have this convex closed set. And what we do then is we use this convex closed set to look at lower and upper bounds for the probabilities of certain other events. So we pick another event C. In the example, it was the intersection of A and B. And what we do then is we look at the probability of C, where this probability ranges over all the probabilities that satisfies the bounds. So all the probabilities in this Creel set. And this gives us a lower probability and an upper probability. So what have we done? We've specified certain bounds on certain probabilities. We've looked at all the probabilities that correspond to those bounds, that answer these inequalities. And from that, we derive probabilities, bounds on the probabilities of other events. So what we've done is, in fact, a way of probabilistic inference. We're doing inference. We start from bounds on certain probabilities, and we compute bounds on other probabilities. This is the basics of what we call conservative probabilistic inference. Now, it's important to say something about this. When you talk about this kind of thing to people who are used to working with probability theory, probabilists, the notion of a set of probabilities is alien to them. To them, a probability is given. The fact that you allow probabilities to be free is for a probabilist a bit alien. And this leads to many misunderstandings. It's a point of view that forces you to think in a certain way. What I'm going to do here and try to do is to force you to look at this problem in a different way, to unhinge you a bit. So this was a Creel set, meaning a closed and convex set of probability measures. Later on, we will show that we can let go in some situations of these convexity and of these closeness issues or properties. But that is only later. That is for the end of this day. Okay, so we've come to Creel sets. Let's go to expectation intervals. Because Creel sets are sets of probabilities, and I've already said in the beginning that probabilities may not be the best way to talk about imprecise probabilities. Expectations are already a better way to talk about imprecise probabilities. And in order to explain that idea, I'm going to take you on a small excursion in 3 dimensions. So let's look at a 3-dimensional outcome space. So most of the outcome spaces or possibility spaces, omega, that I will consider today will be 2-dimensional. Why? Because they're easy to draw and they give you a lot of geometrical or visual insight. This is the one problem where I'm going to go to 3 dimensions because, interestingly, when you look at imprecise probabilities, the difference between 2 dimensions or 2 possibility, the possibility space with 2 outcomes, and 3 is enormous. It's incredible. You think you know everything when you look at 2, especially when you're in probability theory. There's not a huge difference between 2-dimensional and 3-dimensional. Imprecise probabilities, it's like an explosion of new and unexpected things that happen when you go from 2 to 3. I'm only going to show you what can happen when you look at an outcome space with 3 elements here on this slide. Most of the other slides will be about 2 because they're easy. So let's consider 3 possible outcomes, A, B, and C. And I'm going to look at functions. I'm going to assume that I have, briefly say a few things about it. I'm going to assume that I have some random variable, some variable x, that takes a value in A, B, and C. And I'm now going to look at the function G, and that is a map from ABC to the real numbers. So in other words, it's a function that associates with each possible outcome a real number. It's an uncertain outcome. Why? Because it's uncertain which of the 3 it's going to be, whether it's A or B or C. And so the value of this term is also going to be uncertain because I don't know the argument. So it's an uncertain outcome, and an uncertain outcome we call a gamble. Now, such a gamble is completely determined by the three numbers, the value in A, the value in B, and the value in C. So those are three real numbers, a triplet. An element of R3. A point in three-dimensional space. So every gamble, every uncertain outcome, if you want, can be modeled, can be represented by a point in three-dimensional space. And so I try to draw a three-dimensional space there. You see three special functions. This one here, this point is a point 1, 0, 0. So it gives me a 1 in A and 0 elsewhere. This function is also called the indicator of A. It's 1 on A and 0 elsewhere. This is the indicator on B. It's 1 on B and 0 elsewhere. It's this one here, this point. And this point is the indicator of C. Now, these are, of course, also constitute a standard basis in three-dimensional space. So any point, any gamble, any reward, any function can be written as a linear combination of these three functions. So any point alpha, beta, gamma is alpha times the first unit vector plus beta times the second unit vector plus gamma sign times the third unit vector. These unit vectors are indicator functions. This is just basic linear algebra, right? Okay. So now, okay. Now I'm going to look at the probability mass function. A probability mass function is a function that gives a probability to A, to B, and to C. So it's also a point in this three-dimensional space. This gives a value to A, the probability of A, a value to B, the probability of B, and a value to C, the probability of C. But it's not just any point, because the probabilities are never negative, so it must be in the first quadrant. All the values are non-negative. And the values must sum to 1, so it must be on the plane where the three coordinates sum to 1. So it must be in this green triangle. This green triangle is called the probability simplex in 3 dimensions. And what we typically do is we will take it out of the 3 dimensions and we'll place it in the plane of transparency. So this is this probability simplex, and the idea is that any point in the simplex, any point in here, any point in here, is a probability mass function. And so all the probabilities, all the probability mass functions, all the possible probability models are points in this 3 dimensions. So take any point in here, any point in here, then the probability of A, here is A, the probability of A is just the distance of that point from that point to the opposite side. The probability of B is the distance, B is here, is the distance from that point to the opposite side, and the probability of C is the distance from that point to the opposite side. And the sum of these is 1 in this triangle. That's one of the properties of triangles. Okay. So this is how we work with probabilities. Now suppose that I that I now impose a probability constraint. I'm going to say the probability of A is 0.5. This is an equation on the possible points. Yeah, it is a restriction on the possible points. All the points that satisfy this restriction are the points for which the distance from that point to the line here, to the opposing line for A, is equal to 0.5. So this is this line. So all these points on this line correspond to the probability of A is 0.5. All the points on this line here correspond to the probability of A is 0.2. In this way, if I say something about the probability of an event, it corresponds to a line in this simplex space. Now suppose that I impose lower and upper bounds on that probability. So I say the lower bound on the probability of A is 0.2 and the upper bound is 0.5, and this corresponds to this blue region in the syntax. These blue region are all the precise probability models, all the mass functions that satisfy the inequalities. And I can do that for B as well. Yeah, so suppose that I have two bounds on the probability of the event B. Yes?
Use a black marker for the board instead of red one, just for the online participant.
Sorry?
Just switch out the red marker for a black marker. This isn't a substance question.
Sorry, you're talking gibberish to me.
The marker in your hand?
The marker in my hand? This one?
Is red. Use a black one.
Ah, all right. That okay.
Sorry, you're in the zone.
Ah, I'm sorry. I was thinking about. I wasn't thinking about markers. Yeah. Okay. No problem. So I have two bounds on the probability of B, and that so 0.2 and 0.3. The distance is then either 0.2 or 0.3, and anything in between is okay. So the blue region is a set of all precise mass functions that correspond to those bounds. And I can do something similar for C as well. So now what I have is lower bounds on the probabilities of A, of B, and of C. If I take them all together, I get a region, a convex closed set. In this case, it's a convex polyhedron of the simplex. And this is my Creel set. This is my set of probabilities that corresponds to the statements with the restrictions that I've made. What do you notice about this Creel set? What's so special about this Creel set? It's an intersection, but it's always like that. Yeah? Any Creel set is an intersection of things, even though it's other, so that's not really special. What is extremely special about this one? If I ask you to draw a convex closed subset, any convex closed subset, would it look like this? Probably not. Yeah. Sure, yeah, that's one thing. That's why I said it's a polyhedron, but there's even something more special about it.
Sides are parallel to the sides of the
sides are parallel to the sides of the simplex. Okay. So this seems to signify that if I impose restrictions on events, the corresponding Creel set will always have sides parallel to the sides of the simplex. Now you will tell me, oh, yeah, you haven't specified all events. You could also, for instance, look at the lower bounds of the probability of EV. And maybe, just maybe, that helps, does it? Does it help? Will it allow us to go through Creel sets that are, whose sides are not parallel? What do you think? Yeah, the complement is a singleton. So this one here is an upper bound for, there's a lower bound for the probability of AB. So it will be 1 minus the upper bound for the probability of C. Yeah. And the same here, this will be 1 minus the lower bound for the probability of C. And so that doesn't help, because I get no new information from this. So, conclusion? If I do this, I can't get all the Creel sets. I can't get all the convex Creel sets. If I were to draw a circle, I wouldn't be able to, or this would not be equivalent to specifying bounds on events. So what do we do? Well, the only way to get to Creel sets whose sides are not parallel is by looking at expectations. Expectations of functions. Let me look at two blue lines. This blue line says that the probability of B is equal to the probability of C. That's a way of saying that. But this is also saying that the probability of the difference between the indicator of B and the indicator of C, that the expectation of that difference is 0. So I'm just specifying the expectation of this gamble indicator of C minus indicator of B. This is the expectation of this, and this expectation is 0. So if I specify an expectation that is 0 in this case, I get this line. Another line here is this one. And what I see is that here the probability of C is 3 times the probability of B. This is 0.6 something. Sorry, yeah. So the point is 4, so this is 0.78 here. That's 75. So this is where the probability of C is 3. So this is C is 3 times as likely as B. This is this line. Again, I can write this as the expectation of the indicator of C minus 3 times the indicator of B is 0. So if I have the expectation of a gamble, what is that? A gamble is, remember, just some combination of these units. So just some combination of indicators. So if I take the side that is parallel to one of the sides of the simplex and I rotate it, then I get something that is typically not parallel to the side of the simplex. Now, what does rotation mean in 3 dimensions here? Rotation means that I start with something that is like IA, and it turns into something, to a linear combination of these vectors. So rotating means turning this IA into a linear combination of them. And so in order to get things that are not parallel, I have to rotate, and I need to look at expectations of gambles. So that's the idea. So this is why, if we want to look at imprecise probabilities at general real sets, the language of probabilities is not strong enough, in a sense. It's easier to work with expectations rather than probabilities. In the precise case, expectations and probabilities are equivalent. If I have a probability measure, I can define an expectation. If I have an expectation functional, I have a probability measure. They're just 2 sides of the same thing. In imprecise probabilities, typically, we will use either sets of probabilities, or if we want to work with single things like lower probabilities or lower provisions, then typically we will have to work with lower expectations, because lower probabilities are not strong enough. Our language of lower probabilities and upper probabilities is not strong enough. We need lower and upper expectations. Okay. So this brings us to the notion of expectation intervals. I have an expectation, and I'm going to give, in some way, like before, I had some events, and I had an assessment, what we call an assessment. So that's just some lower and upper bounds for the probabilities of certain events. I extend this in this new way to an assessment where I give lower and upper expectations for certain gambles. So I'm replacing probabilities by expectations. Again, I have a creedal set, all the probabilities, all the precise probabilities that satisfy these qualities. And once I have that creedal set, I can now look at what I call the lower and upper envelopes. I take any gamble, I calculate its expectation for some element of that creedal set, and then I let that element range over the entire creedal set. I will get a set. The minimum of that set is called the lower expectation. The maximum of that set is called the upper expectation. So what am I doing? I started with an assessment of lower and upper expectations of certain gambles, and I derive the lower and upper expectations of any gamble. I'm doing a type of probabilistic inference, inference. again. And the first one to really study this and realize this in its full detail was Peter Walker. Probably looks much different now, but I don't have any recent picture. These are pictures when I was young, so he must be ancient at this point. Okay. Right, so this brings us to lower and upper expectations. If I have a creedal set, and go back. If I have a creedal set, then using this procedure, taking the expectation of a gamble, and then letting the probability range over the entire creedal set, and looking at the minimum and the maximum value, allows me a way to calculate the expectation, the lower bound on the expectations, or the lower expectation, and the upper bound on the expectations, or the upper expectation of any function g, any gamble g. I can do that now. If I have a creedal set, I can do this. Turns out that these expectations satisfy a number of very simple properties. They're always bounded by the infimum, by the smallest value of the gamble, the minimum of the gamble, bounded below. The expectation, the lower expectation of a sum always dominates the sum of the lower expectations. And if I have a positive constant, I can take it out of the lower expectation of it. Those are the three defining properties of what we call a lower expectation. So what we now do is we're going to work the other way around. Rather than starting from creedal sets, starting from sets of probabilities, we're now going to define a lower expectation as anything that satisfies these three things, these three properties. And you can show that they're equivalent. Yeah? There are two ways of saying the same thing. If I have a convex closed set of probabilities, then my lower expectation will satisfy these, the corresponding lower expectation will satisfy these three properties. If I have anything that satisfies these three properties that corresponds to it, a creedal set, a convex closed set of probabilities. All the probabilities that dominate the expectation. Yeah? So there's a one-to-one correspondence between convex closed sets of probabilities on the one hand, and these lower expectations. You can do it the same with the upper expectations. Upper expectations satisfy similar properties, but there's an interesting property called conjugacy. I needed to use black instead. And black is here. Okay. This is cool. So how can I make this black? No, that's not the way. Cool. Cool, Arthur. Is it a whiteboard? Jeez, it's here. Where? So look at the upper expectation minus a gamble g. By definition, this is the maximum of all the expectations associated with P minus G, where P is in my creedal set. The expectation of minus G is minus the expectation of G. That's what expectations do, right? And the maximum of a minus becomes minus the minimum. And so this is equal to minus the lower expectation, G. So what we've derived is a relationship between the upper expectation of a gamble and the lower expectation of minus that gamble. So if I load the lower expectation functional, that immediately gives me the upper expectation function. And this relationship is called the conjugacy relationship, this one. Upper expectation of a function is minus the lower expectation of minus that function. That's the conjugacy relationship. And so if I know a lower expectation, I immediately have the corresponding upper expectation. Okay. If you want to know more about these interesting mathematical models, and if you want to know more about the mathematics of this, I can recommend this book that Matthias Sofas and I wrote about them. It's called Global Previsions, where prevision and expectation, for the purposes of today, will mean the same thing. We'll have to say something more about the difference between a prevision and an expectation later on. But for the purposes of this lecture now, yeah.
So why is the first property should be equal? Because it's close to convex.
Sorry,
The first property of lower expectation.
that it should be equal to the infinite?
Yeah. So you take the mean of the close convex.
Yes.
That's the input path, not the input the value.
It's the input of all the possible. So it's the inf of all the. Well, let me go. I show you here. The lower expectation of this of this gamble, the indicator of A is 0.2. The minimum is 0. It should be equal to 0. Just a short, small counterexample. It's because you take the minimum not over the entire simplex, but over a subset, and that makes. If you take the minimum over the entire subset, then you will get the minimum. Yeah. All right. Let me go on. Fine. So this is lower and upper probabilities, lower and upper expectations. Let me go on to this vision later. If I have a lower expectation, then I can look at something at gambles. So this a gamble is an uncertain outcome. It's an uncertain value. And I will say, I will define an ordering on these functions, on these what we call gambles, these functions on the uncertain outcome. And that ordering is defined by f is strictly greater than 0, if and only if its lower expectation is greater than 0, or the gamble itself is greater than 0. So drawn in this two-dimensional space, if I have a gamble, an outcome space with two possible outcomes, A and B, and all the points here are all the functions, all the gambles. So any point is a gamble. A gamble will be better than 0 if it's here in this first orthant without 0. That is this, what this means. F is strictly greater than 0 means it's in this positive orthant without 0. Or its expectation F is strictly greater than 0. Now you can prove, we'll come back to this later, that the region where the expectation is strictly greater than 0 is a cone, convex cone. Something that is closed under positive linear combinations. And so linear combinations whose coefficients are positive. This is a convex cone. This blue region is all the gambles that are whose lower expectation is positive. So if the lower expectation is positive, it means that since a lower expectation is a minimum of expectations, all the expectations are positive. So this is why I think that this is better than 0, because all its expectations, all its candidate expectations are strictly positive. Yeah.
It's only a convex cone. It doesn't need to be closed, or it doesn't matter.
It's open in this case. It is an open, it matters, but not yet. But it is open at this point. This is why I have these dashes here, because it's open. Open. But at this point, it's not really important yet. Okay. Yeah. Now, I will define, this is an ordering between F and 0. I'm allowed to compare F and 0. I'm going to assume that this ordering, I'm going to justify it later, I'm going to assume that this ordering is a vector ordering, which means that it is compatible with addition. So let me just briefly. Something is a vector ordering. If F is greater than G, this is equivalent to F plus H is greater than G plus H, and this is for any H. So I can add any constant vector, and it won't matter. It won't change the ordering. That is what we call compatibility with addition. It's a vector ordering. Okay, so this means now that if I have G is greater than F, and I assume that this ordering is a vector ordering, I can subtract G from both sides. So I find that G, is that it? Yeah, or I will subtract F from both sides. So I have G minus F will then be greater than F minus F, which is 0. So this is equivalent to G minus F being greater than 0. So this is what I have here. G greater than F, if and only if G minus F is greater than 0. And now if I replace G by 0 in here, I find that 0 is better than F. Let G be 0 if minus F is better than 0. So this is what I'm after. And minus F better than 0 means if I plug in minus F into this condition, it tells me by conjugacy that the upper expectation must be smaller than 0 or F must be smaller than 0. And I get this blue region here. This is the blue region where F is worse than 0. So the green region is F is better than 0. I prefer F to 0. And this one here means I prefer 0 to F. And anything in between is what I call indecision. It's not entirely correct, and I will come back to it later, but at this point, these are the gambles where I have no decisions. These gambles are not better than 0, and they're not worse than 0. In a sense, I can't compare it with 0. In some sense. Okay. Yeah.
What is F in relation to A?
F is any function. So F is a gamble, is a function on the possibility space A. It's going to be so it can be represented by a point. As I said, any gamble, any function is a point in the n-dimensional space, in this case, 2-dimensional space. So the gambles are the points. Green region is the points, are the functions. So the points where that satisfy F is strictly better than 0. The blue region are all the gambles, all the points where that are worse than 0. And then this white region in between is where I have nothing. So I come to indecision. Yeah.
So here is the coordinate of A and B is the probability. It's A and
No, the value. The value of F. So it's important to make this entirely clear. If I have a point here, it has 2 coordinates. This is the value of the function or the gamble in A. This is the value of the function in B. Yeah? So just any function F has 2 values in this case, in A and in B, and so it can be represented by a point in 2-dimensional space. So any point is just a way of representing a function on that space. Yeah. Good. Any probability that is in my creedal set, any probability that's in my creedal set that corresponds to this expectation functional, so my expectation corresponds to a creedal set, any probability in that set has an expectation, and the expectation being 0 is this red line. So this red line is the points where the expectation is 0 for any probability in this Creedle set. So here is the expectation of that gamble as. So this is where the expectation is 0. So there's a number of red lines in between this white region. And all these red lines represent elements of the Creedle set that corresponds to my expectation. Okay. I'll come back to that later as well. And this idea, things being better than 0 or worse than 0, is now taken a step further. It's taken a step further to the idea of a desirable gamble. I will not assume from this moment on that you have an expectation operator or a probability or a set of probabilities or a lower expectation operator. I'm not going to say assume anything. I'm leaving probabilities and expectations behind. I'm going to start from the notion of something is strictly better than 0. And so I'm going to look at any gamble or any function. So gamble means any function on the possibility space, in this case A and B. So any point has 2 coordinates FA and FB. Any such gamble, I'm going to ask you as a subject, a decision maker, do you strictly prefer this gamble to 0? Is this gamble strictly, yeah?
The gamble 0 is not taking the gamble.
Sorry?
What is gamble 0? What is 0?
0 is nothing. Yeah, so at this point means that this is a 0 gamble. It gives you 0 if A occurs and 0 if B occurs. So it gives you nothing. It's the status quo. It's nothing. Yeah.
Equivalent to not taking the gamble.
Yeah, equivalent to nothing, right? Not changing. So if you take this as a gamble, as an uncertain reward that you will get, then your capital will not change. Your utility will not change for this time. Yeah. So 0 is the status quo. It's nothing. In this sense. It's good of you to ask to clarify this. Fine. So I have a gamble, an uncertain outcome. I don't know what its value is going to be. And I ask myself, is this better than 0 or not? Is it strictly better than 0?
The options which are worse than 0.
You think it's worse than 0? I don't want it. I don't want to engage in this gamble because it's worse than 0. I wouldn't want it. If you were offering it to me, I would say no.
Can I make one comment?
Sure.
I think maybe one source, the confusion here, or the source of the question is between changes isn't already final utility. So 0 isn't the final utility. It's not a minimum possible final utility.
No, it's like zero change in utility.
So -1 isn't somehow worse than a minimum sort of possible outcome. It just means a reduction.
Yeah. Let me further try and clarify it because it's important for what's going to follow. So when I talk about a gamble, this is you are uncertain about something. There will be an experiment. Let's say. So fix this in your pass with the coin. And I tell you, you will get 1 on heads and -2 on tails. That could correspond to A is heads, B is tails. This gamble here will give you 1 on heads, -2 on tails. If this is a fair coin, will you accept that gamble? Probably not. Because if you know something about probabilities, the expected value of the gamble is negative. You probably will not accept it. So it's worse than 0. You will not take the gamble. So rather than think about what are your probabilities, I'm going to ask you to think about what gambles will you accept. You will strictly prefer the 0, what gambles will you reject. This is the language that we'll be talking about. So the idea is then that we start with simple statements of the type, the gamble is desired. you as a subject, you prefer this gamble to 0. You will accept it if it's offered to you. And even better, more than accept it, you strictly desire it. It's strictly better than 0. In some way. And so what we're going to do now is start from those statements. We're no longer going to talk about probabilities, we're just going to talk about those types of statements. Take a gamble F, any point in this space, do you accept it? Do you think it's desirable? If you do, you'll say, to me, F is desirable. And we'll make it into some sort of logical statement. To me, F is desirable. And those are, and so this brings us to a logic of desirability, because I'm going to try and combine statements of this type, elementary statements of this type, according to some rules. I'm going to introduce a number of axioms that are made quite reasonable by the example of lower expectations that we had before. So first of all the gambles that are desirable constitute a convex cone. That means that if I can add them, if I have two desirable gambles, then their sum is also desirable. And I can multiply them with positive constants. So they're closed under positive linear combinations. They constitute a convex cone. And so if I have a gamble that is desirable, and I take any positive multiplier lambda, then multiply the gamble with lambda, it's also going to be desirable. Yes?
If that multiplier is negative, then the gamble becomes undesirable.
Yeah, that depends. Yeah, typically undesirable. I haven't defined what undesirable is. I've only defined what desirable is. So in order to answer that question, I would have to make a distinction between not desirable and undesirable, which is not necessarily the same thing. Right? So I would need to define undesirable. But in this case, it would not be desirable.
Okay. Yeah. Let's say that F is symmetric, so if you multiply by minus, it can be.
If it's symmetric, well, it will probably end up in this. It is.
Yeah, but I think the expression was if you multiply F by minus,
Yeah.
it becomes undesirable, right?
Not desirable. Not desirable. Yeah. Yeah. Okay, so that's the logic. I'll have much more to say about this later also. Okay. Now, we'll say a few things later about what this logic is, how it works, but my claim is that this logic, the logic behind desirable gambles, is a logic that underlies all of probability theory, at least all of finite probability. So this is the logic that is the conservative inference that is underlying probability. First of all, I can define expectations from this using a very simple formula. The lower expectation is the highest, the supremum alpha, for which F minus alpha is still desirable. Let's unpack this equation. F is this uncertain reward. It's a gamble. Alpha is a real number. It's a constant reward. Whatever happens, I get alpha. Minus alpha is I lose alpha, whatever happens. So minus alpha is a price that you pay. Alpha is the price you pay, which means you lose whatever happens, you pay that price. So you lose alpha, which means you get minus alpha. And F is what you get. So F minus alpha is the reward for a transaction where you buy, where you get F, and you give away alpha. So you buy the gamble F for the price alpha. And so the lower expectation of F is the supremum buying price for that gamble. The supremum constant amount of utility or money, if you want, that you want to give in order to get the alpha in your possession. That is your lower price or your lower expectation. Yeah.
Is there a reason that you use this UP instead of max?
Sorry, no. Yeah. The reason is that, well, for instance, here. Here, for instance, if here, the border is not in there. Yeah, not necessarily in there. Yeah, I'm not necessarily including the border. And then it might be that the supremum is not in the set because it's never reached. Yeah, this is why we use a supremum rather than a maximum. If it were closed, then we could use a maximum. That's not necessarily closed. Very good question. Okay, so then this gives us lower expectations, starting from sets of desirable grounds, from this desirability notion that we have here. Interestingly, I can also define, yeah. Oh, sorry. Yeah.
When you say define expectations, you mean there's like a one-to-one correspondence?
No. I'm just, the idea was forget that you know about expectations, forget that you know about probabilities, forget everything you know. I'm now starting from scratch with this primitive notion of desirability, and I'm defining expectations in this way. And they will have, yeah, Paolo, indeed, yeah. So the question that Paolo asked was, if I say F minus alpha, what I really mean is alpha multiplied by the constant gamble that gives you 1 everywhere. Yeah? So I denote alpha. Alpha to me is just the constant gamble that gives you 1 everywhere. Alpha everywhere. So that's my notation for that gamble. Interestingly, I'm not going to do this as an exercise later on today. Bayes' rule can also be derived from this, so conditioning can be derived from this by using the notion of a cold off gamble. So I'm going to use this formula. And using this formula allows us to define conditional expectations. Later on, I'll explain everything. And you can show that Bayes' rule is a special case of this, especially we cover Bayes' rule. It will be an exercise later on. Okay. So what this tells us is that if we allow for imprecision, once we allow this idea to take root, then we can lay bare this conservative inference mechanism that is lying underneath all of probabilistic reasoning. If we don't, if we only use precise probabilities, then this conservative inference mechanism remains hidden. We don't even think about conservative inference. A probabilist will never think about conservative inference because his probabilities are there. Why would he make inferences about them? They're given. Yeah? So it's only if you allow yourself to think about imprecise partial probability that you can get to the logic behind probabilistic reasoning. Okay. One more thing that I'm going to talk about today. What time is it, by the way? How much time do I have left for this session?
35 minutes.
Okay. Yeah. I'm going quite slow, but I think it's good as an introduction. Because these are themes that will be elaborated later on. So, this is desirability. We can now move to something more complicated, which is the idea of choice. So what we had, what I've been discussing up to now is what we call binary choice, where I compare two things, two gambles. And I say one gamble is preferable to another gamble, or one gamble is preferable to 0. So what I'm doing is binary comparisons, binary relations between two gambles, preference relations. And so that is the logic behind this binary choice. This is the action that I wrote down on the previous slide. There's also something like non-binary choice functions. And so we can get, and I'm going to explain this later as well, I'm just going to mention it here, we can get to the idea of non-binary choice by extending this logic, by adding to this logic or statements. So far, I only have and statements. I have one gamble is desirable, and another gamble is desirable, and another gamble is desirable. So if I restrict myself to and statements between desirable gambles, then what I have is simple imprecise probabilities, expectations, probabilities, lower expectations, lower probabilities, desirability of word. If I add or statements, if I add an axiom that says if I have a number of gambles, f1 through fn, and if at least one of them is desirable, then I will call the set desirable. So I introduce a notion of a desirable set. The set is desirable if at least one of its elements is desirable. By adding that notion, you can get to something much more interesting, like a logic, a propositional logic with statements like F is desirable. You can show that this propositional logic is actually, in a certain way, equivalent to much of what's done in choice theory, in theory of choice functions. Okay, I'll come back to that later. Okay. So this was desirability in a nutshell. Now, what happens is, this is static. I'm looking at one variable, looking at one uncertain experiment. What happens if I extend this, if I go from one experiment to multiple successive experiments? I look at the outcome of an experiment, a coin flip, at time 1, another coin flip at time 2, another coin flip at time 3, and so on. In that case, what we have is a stochastic process. So I have a number of variables, x1, x2, x3. Capital letters here mean I don't know. So this is a time-honored tradition in probability theory. If you write a capital letter, it means that it is uncertain, that it is random, that you don't know it, that you don't know the value. So x1 is a variable in some outcome space, let's say 0 and 1 here. Yeah, I have two possible outcomes, 0 and 1. So coin flip, where 0 is heads and 1 is tails, for instance. And then I have an outcome of a coin flip, which is unknown at time 1, at time 2, at time 3. I can depict all the possible outcomes of this sequence of coin flips in a tree. This is what I'm doing here. So this little square here is when nothing has happened yet. And then I have my first coin flip and I have two outcomes, 1 and 0. If my outcome is 1, then my second coin flip has two outcomes, 1 and 0, and so I get here or here, and so on. So all the possible sequences of outcomes are depicted in this, what we call an event tree. So this event tree is a way of representing all that can happen, and you flip those coins and keep flipping. The nodes in this event tree I will call situations. So any blue thing in this event tree is a situation. It is a finite string of zeros and ones. So 1 or 101 and so on. So a finite string of zeros and ones is a situation. And if I have an infinite string of zeros and ones, so if I keep on going in this tree and keep on going and keep on going, then I have an infinite string of states, and I will call that a path. The path is just an infinite sequence of zeros and ones, and I will collect all these infinite sequences of zeros and ones in my sample space omega. So omega is the sample space of my infinite experiment. Yeah. So any path is what could happen if I flip this coin an infinite number of times. All right. Something that we will also have to do at some point is look at what is a stochastic process. A stochastic process in this case, is just attaching a real number to each of these situations. That's what we call a stochastic process. So I attach a real number to each of the situations. And that's it. So I populate this tree with real numbers. Attach a real number. It need to be the same, it can be different in every situation. Now, okay, so this was an inventory. What can happen now is I'm going to, in each situation, I'm going to attach to that situation a probability model. A probability model for what is going to happen immediately after that. So here I see the outcome of my first variable, it's a 1. And then I'm interested in what's going to happen next. So what's the next outcome going to be? What's x2 going to be? It can be either 1 or 0. And I'm attaching a probability for 1 here. That is my P1. Here, after observing first a 0 and then a 1, I can also specify my probability for whether it's going, the next one is going to be a 1 or a 0. And I denote that probability by P01. So I can have a different probability model in each of the nodes. It means I can learn. Because by observing where I am, I have 1, 0, 1. Okay, in 1, 0, 1, I may use a different model than in 0, 1, 0, for instance. So I can change my behavior, my model, after observing what I've seen before. This is what happens in such a probability tree. So you have a probability mass function for the next outcome. In each situation, you have a probability mass function for the next outcome. And it can change according to where I am. That is what we call a probability tree. How do I make that imprecise? Well, instead of having a precise mass function, I can have a lower expectation function. Or I can have a set of desirable gambles. Or I can have a set of mass functions or a set of probability measures there. Instead of a precise model, I can attach an imprecise model to each node in the tree. I can do that. Why wouldn't I be able to do that? So this is how we deal with stochastic processes that are imprecise, that have imprecise probabilities. And we can do inferences on such stochastic processes. Let me give you an example. Just going to give you an example. A Markov chain. A Markov chain, imprecise Markov chain, how do we define that? Well, remember, I have a mass function or a set of mass functions or an expectation operator or a set of desirable gambles in each of the situations of the tree. And it can be different in each of these situations. But if it satisfies this, what we call a Markov property, then we call this an imprecise Markov chain. What is the Markov property? That says that the model that I have after observing a sequence of outcomes x1 through xn only depends on the last outcome. So my model here, M10, only ought to depend on the last outcome, so only ought to depend on 0, so it ought to be the same as the one here. That is what happens. So here, I have a model after observing 1 and 0, and this model only depends on the last outcome, so it ought to be the same as this one. And the same here, the last outcome was a 1, so I ought to have the same as this one. And so, everywhere in the tree. This is what I call an imprecise Markov chain. Yeah. Now, oops. How do we do inferences in general in these models, in these dynamical, what we call dynamical models, where they have many things happening one after the other. How do we do inferences? Well, the idea is, suppose I have, in each situation, I have a set of probabilities. Yeah, this is my model. What I will do is, I will select, in each of these situations, I will select one. It's a set of probabilities. I will pick one in each situation. So there's many, many choices. Okay. In that case, if I've done that in each situation, then I have a normal standard probability tree. And I can do all calculations that I do in a normal probability tree. So we know probability trees, we know how to work with them, we know how to calculate with them. So I can do that. I can do my inferences in that tree. I can calculate probabilities or expectations somewhere. Okay, that is for that one choice. I will repeat that for another choice in each of the situations. And do the inference again. Get another outcome, and so forth, and so on. Until I get all the possible choices, and then my result will be a convex set of outcomes, that will have a lower and an upper bound. And in this way, I can calculate the lower value and the upper bound. And in order to do that, what I have to do is I have to do an infinite number of choices. And the number of choices, even if it is finite, if I can restrict myself to something finite in each of the nodes, even then it will grow exponentially in complexity. So typically, doing inferences in trees like this has exponential complexity in the number of steps that I have to take. So this is not very useful. Yeah? Sorry?
Which topology have you used to determine that it's closed?
Sorry?
Which topology have you used to determine that it's closed? The set of super martingales. Is it the topology?
Oh, okay. I'm not talking about. So ignore this. Yeah, I'm just looking. I'm not talking about. I'm talking about that later. But you can show that it's closed, but that is another thing. So I'm not going to go into that at this point. Sorry. Yeah. So it is very complex to do that. Okay. Now in the case of imprecise Markov chains, where you have this additional condition here. You can show that many inferences there no longer are exponential in complexity, but have polynomial complexity because of the Markov condition. And so you can, in that case, we can still do efficient calculations. Now suppose that you're doing a calculation in a precise Markov chain. But say, for instance, that Markov chain is time varying, so you have a different model that can change in time. That's possible too. And your calculation will be difficult. Now, suppose that instead of doing that for the precise Markov chain, you do it for an imprecise Markov chain where your set of models is the same everywhere. So it doesn't change where I am, it's the same everywhere, for instance. Or it's not time invariant. But it's imprecise because it has to contain all the models. Whereas the first inference was complex because these models change in time, this one can be done with polynomial complexity. Only the result will be imprecise. You will have a conservative inference. The real result will be in there because of what you've done. You have made sure that all your models are inside the approximations that you've used. The real results will be in there. So what you have is something that you can compute efficiently, quickly, polynomial time, as a conservative, guaranteed to be correct approximation for something that is difficult to compute. Keep that in mind. It's going to come back many times. This is one of the reasons why imprecision can be useful. because you can use efficient calculation methods to compute conservative bounds of things that you're not able to compute because of the complexity in the precise case. So you can calculate for thousands and thousands of years and you never get to the precise results, but you can get a good approximation, a reasonably good approximation in much shorter time. That is one of the advantages of imprecise models. And this brings me to this here. Yeah? The three things: accuracy, precision, and simplicity. Sometimes what you want is to be accurate, which means that your calculations contain the right results. You would like it to be as precise as possible, and you also want it to be as simple as possible. And the idea is that there is often a trade-off between precision and simplicity. Sometimes, often, you can, by decreasing the precision, so increasing the imprecision, and decrease the complexity of your calculation. So you can often get good approximations for things that are very hard to calculate precisely. And this is one of the positive reasons for using imprecise probabilities in precision. What time is it? It's about time, right? I'm going to skip the thing about algorithmic randomness because I'm going to talk about that later on anyway. I'm going to go through, because I think it's enough already. I see you getting tired. I'm certainly getting tired. And there's a lot more to come in the afternoon and in the coming sections. So is it okay, Jason, if I extend the break somewhat?
Absolutely.
Absolutely.
We need to manage ourselves. This is a.
Or I can start with
This is a marathon, not a sprint.
or I can already get started with the next one.
Let me go check if the copies there.
Okay, in that case, yeah, we can give ourselves some extra time, if you don't mind. But there's a summary. So before you go and dive for coffee, what I want to say is that if we allow imprecision in probability, we can, first of all, deal honestly, in the sense that we accommodate for it, in the sense that we realize it's there and we try to take care of the consequences. So we deal honestly and systematically with incompleteness and with indecision and with imprecision. Something that I haven't talked about is that if you look at, from a pure mathematical point of view, if you look at the mathematics of imprecision, if you look at the mathematical models that we see when we allow for imprecision, then the precise models will always be special cases of those more complex, larger mathematical models. And it's often very interesting to look at these mathematical models that are more complex and more and wider, because they tell you why, often tell you why the thing that is so special for precise models, why it is the case, because you're allowed to look at a much wider landscape. You're allowed to see many more things, and you can see the reason for many funny things that happen in precise probabilities. You can see that, for instance, they don't happen generally in imprecise probabilities, and they only happen, just looking at an example, they only happen in the precise case. To give you an example, independence, for instance, is something that is very specifically defined in precise probability theory, whereas in imprecise probability, it explodes in like a multitude of different notions, each with a different meaning. And all of these coincide for the precise case. It's often not really, or not obvious why it should be so. For instance, to give you an example, in precise probability, if one event, if independence is a symmetrical notion, if one event is independent of another event, then that other event will also be independent. It's completely symmetrical. It doesn't have to be that way. I mean, it's funny that independence should be symmetrical. One thing is independent. If one thing is not dependent on something else, why should that be symmetrical? It's not necessarily the case in a number of imprecise models for linear movements, but these collapse and precision enters the picture. Just one example. There's many, many more where you see interesting things, interesting structure that is there in the imprecise theory, and then you see why certain things happen in the precise theory as well. It's always better to widen your point of view to see more. That's why we travel. Okay. What else was there? Okay, yeah. Another thing that I pointed out is that we can look at the logic behind probabilistic reasoning. It just jumps out. We didn't have that when we were only looking at precise probabilities. But as soon as we look at imprecise probabilities, this logic comes to the fore. Something that I haven't talked about, classical measure theoretic probability that you all know and perhaps love. It's very closely related to a new branch of probability theory that is called game theoretic probability. And it's imprecise probabilities that allow you to see the link between the two more exactly. And then the final one, this is one that I've already hinted at with my figure, revolves. It allows us to look at simpler and more conservative models for things that are hard to compute or hard to calculate when they are precise. So those are the number of positive reasons for using imprecision. And in the coming lectures, I'm going to go into more detail in each of these things. So it's good that you now know what I'm going to talk about. And then later on, we will go into a bit more detail. And we'll also do some exercises because now you've been you only had to ask questions, and then I can get to reverse that role and ask questions so for you to answer, which is much more fun for me. And I hope for you as well. So how about that coffee? Is that no? Anyway, I'm done.